Thanks a lot for the invitation. So today we'll talk about some application of Ricci Flow to the scalar curvature, at least to my understanding, those applications to the scalar curvature geometry. Okay, so let me start with some motivation. So I'm mainly motivated by these questions, which I want to say. So suppose we are given a sequence of Riemannian manifolds smooth, okay, with certain curvature constraints. So we want to understand the following few questions. First of all, the most important thing is whether the limit exists or not after passing to the subsequence, and how regular is the limit is. So certainly we can't expect X to be a smooth manifold usually without a strong curvature constraint. So the regularity of the limit is a big problem. And then, of course, you should ask in what sense of topology, what sense of convergence that you can expect. And of course, finally, can you identify the limit under certain kind of a weak convergence? Okay, so this is a very vague question that we want to ask. Okay, but of course, depend on how the assumption you are imposing on the question. Okay. So this kind of question is well understood when you consider the really strong curvature condition like the sectional curvature. We can make use of the Alexandria space theory developed by Man-Chun Lee. And if you consider the Ricci curvature, I normalize the lower bound to be -1. Okay. So then the theory is also well understood by using the optimal transform, and then developed by Johnner, Villani, Sturm, etc. So, and then develop the CUHK coding theory and the RCD theory, which are very hot topics nowadays. Okay. But anyway, the overall summary is under these two really strong curvature conditions, we have compactness. If we have volume long collapse, like talk of Peter toppings, or sometimes even the collapsing case. And also the convergence, the sense of convergence is measured in terms of the Gromov-Hausdorff convergence. Okay, if you also couple with the measure, then it's a measure Gromov-Hausdorff convergence. And more importantly, to me, although the limit is weak, it's only converging in the Gromov-Hausdorff sense, but we can still make sense of the curvature. Okay, the curvature lower bound is still well defined, depending on which theory you're at. Okay, if you talk about the Alexandria space, you can talk about the sectional lower bound in terms of the triangle. And then if you talk about Ricci curvature, you can make use of the RCD theory, okay, to talk about the Ricci curvature lower bound for the metric limit. Okay, but what I want to focus on today is the scalar curvature. Okay, I'm mostly interested in the scalar curvature. And before we move on, we go back to the earlier question that I raised. Let me start with the model case in scalar curvature. So in Ricci geometry, we know the volume comparison, which says that Ricci log negative, if the volume is controlled by the Euclidean, then we know the manifold is flat. Okay, this is the standard Riemannian volume comparison theorem. Okay, and then because I want to ask similar question in scalar curvature geometry, so I would like to draw some rigidity properties related to the scalar curvature. Okay, so the most classical one, to my understanding, is the result by Gromov and Lawson, Shui and Yao, which says that on the torus, if the metric has non-negative scalar curvature, then it's automatically the flat torus. Okay, of course there are some generalization to the spherical manifolds or the connected sum of the torus, etc. But let me just focus on the baby case, the torus. Okay, this is the torus rigidity. And then on the long compact case, we can ask the same question, quite similar to the torus rigidity, but on the asymptotically flat manifolds. Then we know the mass basically controlling the fatness of the manifolds. Okay, and I also want to draw the attention to the rigidity of the sphere, which is a result by Leroux, which says that if a manifold M is spin at a distant non-increasing function f with which is non-trivial, then the scalar curvature lower bound, the spherical lower bound will automatically imply f is isometry. Okay, so these are all the basic rigidity theorem in scalar curvature. Okay, to my understanding. Okay. So let me go back to the first question, but specify to some special case. Okay. So now I consider like I said, I consider the case when the scalar curvature is bounded from below by sigma, say for example. Okay, sigma can be a function or a constant or function, etc., depending on which setting you're interested in. And then, okay, so I'm interested to ask, suppose the sequence of Riemannian manifolds is, I fix the topology of the sequence, okay, to make our life easier. Okay, the question is still interesting enough to me. And then just change the metric, okay, a sequence of metric changing, okay. But if for some reason we know it converges to a smooth metric, okay, but weakly in weak topology, then can we still conclude that the scalar curvature lower bound is preserved? Okay, so interestingly, like some of our discussion in the after the previous talk, we know this is true if the convergence is if this convergence is a CCO convergence. Okay, and in fact, the sigma here can be a function defined on the manifold M, but not necessarily a constant. I just make it a constant to make our life easier. Okay, this is a proof by Gromov, which spill on the fact that we can formulate the scalar curvature lower bound by the CCO, by the inner product structure of a metric locally. Okay. So let me just raise one consequence when we apply to this scenario. So if for some reason, if we know this, if the sequence of Riemannian metric is of almost non-negative scalar curvature on the torus, then in this setting, we know the limit will be a flat torus. Okay. In fact, this is even true if G infinity is a continuous metric, not necessarily a smooth metric by the result of Kim. Okay. And then one more thing I want to point out, this theorem will be false if we weaken the convergence to the distant convergence, okay, in higher dimension. Okay, this is we have, I know Gromov has also have a example, but we have an example building on some of my earlier work with Aaron Neighbor and Warburton. Okay.
So distance convergence, it means Gromov-Hausdorff distance convergence?
No. Because Gromov-Hausdorff distance, we need to fix, the topology can be changing, but now, I mean, we fix the topology and then the distance will converge as a function on M. Yeah. I mean, the topology is not changing. The topology is still M.
Okay. Yeah, thanks.
Yeah. Okay, so because of all this, we're trying to ask for the generalization of the result of Gromov. Okay, try to ask, can we, to what extent we can relax this, we can generalize this theorem. Okay, although we are certain that in high dimension we can, we have to find some intermediate or something in between distant convergence and CCO convergence. Okay, so, but before I move on to the result, let me point out there's another proof by Blummer, which is based on the Ricci Flow. Okay, so far nothing is related to Ricci Flow, but now I'm trying to employ the Ricci Flow techniques, okay, which play the role of regularization. Okay, so the Ricci Flow is a deformation of metric along the Ricci direction, negative Ricci direction. So the most important feature why it useful in the scalar curvature geometry is because the scalar curvature evolves nicely. Okay, the inhomogeneous term is super nice. Okay, and of course, the Ricci Flow preserves lots of non-negative curvature. Okay, but not sectional in all dimensions. And one more things, which is good or bad depending on what question you are focusing on. So the Ricci Flow by itself is a weakly parabolic system. So and it's diffeomorphic invariant. So okay, if you are interested in question like the regularity of Ricci lemma space, then we are in good shape. Okay, because it can't detect the diffeomorphism. Okay, but for us, like the scenario of CCO convergence, to make sense of CCO convergence, we need to fix a coordinate chart or coordinate system. Okay, which makes Ricci Flow techniques not super helpful if you try to use it directly. Okay, and then to fix the problem, we fix a gauge and consider the so-called Ricci-DeTurck flow, which is diffeomorphic to the Ricci Flow, but we involve in some sense we are just fixing the coordinate system of Ricci Flow. Okay, so this is a Lee derivative of metric, and then this is in terms of PD, this is a strictly parabolic system. Okay, so which plays super well in terms of PD theory. Okay, once you fix the coordinate, it's super well behaved. Okay, but it depends on you have a choice of fixing the gauge. Okay, so but on a fixed manifold, on a compact manifold, they're all equivalent. So I would usually just fix one of them. Okay, randomly depending on randomly. Yeah. Okay, so go back to the theorem by Gomov and the approach by Blama. Okay, suppose we are given a sequence of metric. I put a 0 here because I want to emphasize we are trying to flow it. Okay, this is the original sequence of metric that we try to understand. And then, okay, the idea is, okay, because they are supposed to be close to each other. So I just flow each of them one by one. Okay, I mean, I flow the sequence, I also flow the limit. Okay, so I know the sequence and the limits, they're supposed to be close, and they're known to be close in CCO sense initially. Okay, this is the given information. And then we also know that, okay, because the Ricci flow behaves really well, so the scalar curvature low bound can be preserved under the Ricci flow. Moreover, you expect, because we are trying to regularize the flow, regularize the sequence by the flow. So I expect, okay, like the Peter Topping's talk, we expect the flow will be uniformly regular. But because we are fixing the gauge, so we are regular in the sense of PDE. Okay, we for any coordinate chart as a matrix should be uniformly regular. Okay, as a matrix. And then because of this, so we should be able to pass it to the limiting solution, okay, which is still a Ricci-DeTurck flow. But we can't do it at time 0 because you need time to regularize. Okay, that's why you can't get limit or at 0. But as long as you flow it a little bit, you have some room to improve your regularity. Okay, that's why you expect something like this. Okay, based on the philosophy behind. And then because this is a flow, the limiting flow is supposed to be close to the limiting metric in CCO sense. So then the stability should tell us that the limiting Ricci flow should be coincide with the flow that you construct on the limit. Okay. So if this is true, then we can pass the information of the scalar curvature information of this one to this one, okay, in which the limiting Ricci flow, this is a fixed Ricci flow, which can pass T to 0. Okay, although the limiting Ricci flow obtained in this way is not a priori regular at time equals 0, but they are the same after for all positive time. So that's why you can transfer the information of the sequence to the limit and the limit to the given solution, okay, which give you the desired estimate, okay. And as I said, the theorem of Gromov also allows sigma to be a function. And then the important contribution of Balmer is to say that all this also works. Okay, of course, we need argument to make all of them works. And then Balmer also say that, okay, actually we can localize this one like this. Okay, localize it uniformly. Okay, like this, so that the stability also give the localized result. Okay, okay. So this is the result of this is the approach by Balmer. And then as you can see, although the problem is geometric at the very beginning, but the result, the approach by Balmer is quite analytic and should be flexible enough to at least say something different. I mean, it should be flexible enough to get some extension or get some parallel result, okay, because it only relies on some analytic stabilities estimate on the Ricci flow. Although this is a big question in Ricci flow, but seems to be more flexible than the original approach by Gromov. Okay, at least from my point of view. Okay. But why? Okay, I have highlighted all the rest stuff. Okay, this is the things that to be understood. Okay, it's not totally clear why this is true. And then, okay, why we works on C0 stuff. Okay, or in other words, why the C0 topology works in the Ricci flow theory, Ricci-DeTurck flow theory. I mean. Okay, this is based on a series of work by Mao Simon, CUHK, and Kim. Okay, I put everything together. To simplify, I think the earliest result is done by Mao's, and then but he didn't prove the stability result, and then CUHK also proved the stability, but only on metric, only for metric on Euclidean space, and then Kim proved it for the general manifolds. Okay, so the result is say the following: suppose the MH is a smooth manifold with bounded geometry. So if M is compact manifolds, then it's automatically true. And then if G0 is a continuous metric which is sufficiently close to some background, okay, sufficiently close to some background. Okay, which is you can always do it because you can always modify a little bit so that you can approximate by some smooth metric in a C0 topology. Then you can flow it a little bit by the Ricci-DeTurck flow with respect to H, okay, such that the flows still stay close to the background metric, the reference that you fix, and the metric converge back to the initial metric in the C0 topology. And more importantly, the metric will become instantaneously smooth in a scaling invariant way, just like the Ricci flow that discussed by Peter. Okay, but except we have a fixed gauge, so there's a connection here. Okay, because it's not scaling. This is not diffeomorphic invariant. We fix the coordinate system, so that's why we have a connection here. Okay, and on the region where G is smooth, the converger is smooth, which is reasonably expected, and then the solution is unique. Okay, so the highlighted 3 and 5 is basically the red part that to be answered, and then they establish this one. Okay, so of course, you can still ask why the C0 topology make this work, okay, right? Because we want to try finding the extension of all this theorem. So you should ask why we impose C0 sense, but not something else, okay? Or L infinity by Lipschitz, things like this. Why we need to impose C0? Okay, so first of all, although we don't put it in this way, but morally speaking, when I say C0, you can try to interpret this as the following. So if a metric is close to a smooth metric in CCO sense, so because H is a smooth metric, so you can pretend H is a Euclidean space. Okay, in the small, really small scale, is basically the same as Euclidean space if you zoom in a little large enough. And then if it's close to the Euclidean metric in CCO topology, in some sense, that means the tangent cone, the tangent cone in a really, really small scale is almost Euclidean in the CCO topology. So you can also interpret this as a gap theorem, okay? And then the almost Euclidean structure gives you some local regularity, okay, which gives you possibility to smooth it out by the Ricci flow, okay. And then the most important part of the proof is to prove that GT is basically the same as G0 in the same topology. That means the tangent cone structure, the almost Euclidean tangent cone structure is preserved under the Ricci-DeTurck flow. That's why you expect the smoothing happens. Okay, this is the moral behind the result of Miles. Okay, and as I've said, okay, once you can do CCO, then the CCO, once you can do C1, everything is easy. Okay, it's very similar to the harmonic map theory, harmonic map heat flow. But once you can get the energy estimate, the rest are easy. Okay, but the difficult part is to get the C1 estimate, the energy estimate. Okay, but it makes because it's almost Euclidean. That's why you can bootstrap from C0 to C1. Okay, it's only possible if, in general, it's only possible when it's C0 close to some smooth metric or flat metric. Okay, intuitively. Okay, and then the key things which is related to some other application in scalar curvature geometry is the fact that the Ricci-DeTurck flow will converge back to initial data in C0 topology. This is you can think of this as a time zero regularity of the Ricci flow, okay, which is a key fact of all this. As I've said, because GT converge back to G0 in C0 topology. That's why you expect the regularization. Okay. That's why you expect GT is still close to a flat metric in a really, really small scale. And then the regularization will do the rest of that. Will do the rest of the works. Okay. So that's why I highlighted this is a key point of the whole theory in Ricci-DeTurck flow. Okay. And then one another advantage of using the Ricci-DeTurck flow is that in fact the whole theory here, you can see that the scalar curvature only plays the role when we when we want to say that the limiting metric has a scalar curvature lower bound. The reason why this is true because the Ricci flow preserves the scalar curvature lower bound. Okay, and then you can see that you can do the same thing for all other preserved quantities. Okay, like the like the non-negative sectional curvature operator or the isotropic curvature, things like this. They are all all these assumptions will fit inside this approach. Okay. But then we don't have to. Unlike the approach by Gomov, we don't have to find the equivalent definition of curvature definition. We can simply make use of the preservation of curvature preservation of non-negative curvature under the Ricci flow to prove all this theorem. Okay, although it's not geometric enough, but it works. Okay, so let me point out one extension first, which is based on some of my joint work with Huang. So first of all, when I look at this question, I try to ask, okay, can we relax the scalar curvature lower bound to some integral sense? Okay, it sounds so stupid, but there are some motivation behind, because if you take a look on the positive mass theorem with Connor, the proof by Mel, you can see that in fact the core idea of the Mel's proof is the fact that you can do the modification using the conformal geometry, which based on requiring the lower bound of scalar curvature is so small, not in the pointwise sense, but in the ln half sense. Okay, so in the proof of Mel, as long as you can find some metric like this, you can use the conformal method to find a better metric. Okay, this is a common trick in positive mass theorem. Okay, so then you should ask, okay, can we do the same things for Ricci Flow, which makes your techniques more canonical? Okay, because the conformal geometry techniques, it always built on some special modification techniques. Okay, I want to try finding a more unified approach by using the Ricci Flow, and then this is a work with Huang, which says that, okay, under all the same assumption in the theorem of Gromov, but except we change the scalar curvature lower bound from pointwise to integral sense, the critical integral sense. This is a scaling invariant power, the scaling invariant exponent. Okay, if the critical LP norm goes to 0, in fact, you can localize it further. I just use a simplified version of it. Okay, so if the critical LP norm goes to 0, then you can also prove that the scalar curvature of the limiting metric has the same lower bound. Okay. Eventually, the integral LP norm, the integral error will be vanishing. Okay, so the idea of the proof, you can see that. So the core idea is to try to improve the preservation of scalar curvature lower bound, except because this is an integral lower bound, so you need to do some energy argument, which replace the result of Balmer. Okay, it takes a little to work on localize it, but it's not very difficult. So let me not go in too much details, but this is the more idea is to make use of a Balmer idea, but replacing the maximum principle. Okay, so we can prove something else. Okay, so and then all right, so then all right, so afterwards I try to take up think about this question of studying the metric which is the bilipsus. Okay, so in fact I'm basically motivated by question in Gromov lecture logs, but I can't prove it's not. I can only prove some case anyway. So I consider the case when the sequence of metric is uniformly bilipsus, not cis-zero, only uniformly bilipsus. So if it's cis-zero, then I can make the lambda sufficiently close to 1. Okay, but I'm not interested in that case anymore. I'm interested in this case, bilipsus case. Okay, but at the same time, if I know the sequence of metric converge to the limiting metric in some weak sense, then what happened? Okay, then what happens? Okay, why this is interesting? Because in the example constructed by myself and Peter, the example also satisfies the bilipsus properties and satisfy this kind of property in the measured theoretic sense. Okay, if you fix the chart and then just treat the sequence as a sequence of matrices, okay, locally, then the GI will converge to some good metric in the measurable sense, LP sense, L1 sense, some integral sense. Okay, but the distant topology will go crazy, although the tensor will still converge to the correct one. Okay, and then but we can't prove it. We try to prove something, okay, and then we can prove the following. Okay, suppose that the sequence GI is still bilipsus, uniformly bilipsus, and then we try to strengthen the convergence to W1N, okay, which is still not cis-zero. This is the critical case of the Sobolev embedding. So the W1N is in some sense they are not related. Cis-zero can't imply W1N, W1N can't imply cis-zero. Is essentially the parallel case, okay, in the PDE theory. And then in this case, we can still prove the same things. Okay, You can also normalize, you can also localize it like what Balmer did, or you can also change it to the LN, the integral convergence. Okay, but I'm mostly interested in this baby setting. Okay, which is interesting and mysterious to me enough. Okay, okay. I also based on Balmer's idea, except I need to rebuild the whole theory of Ricci Flow and the whole existence and stability theory of the Ricci Flow under this different assumption. Okay, ideally, I hope there are some existence theory only depends on the L infinity estimate. But certainly, if you only have L infinity estimate, you can't expect some estimate to be true. Okay, I will go back to this in a minute. So the theorem, the quantitative version of the theorem, not very quantitative. The theorem states the form, which is basically the analog of Miles, the Simon's result. Okay, so it's a joint web with true, and some of the cases is also done by Name and Simon, which says that, okay, we are in the same setting. MH is a smooth manifold with bounded geometry. So you can pretend M is compact, so that is always true. And then for any lambda is measuring how good or bad the bi-Lipschitz constant is. You can always find an epsilon, so that if G0 is a bi-Lipschitz metric, which is also W1n. So by W1n, I mean the tensor, the matrix tensor. The metric matrix is W1n in the coordinate. Okay, such that the gradient of G0 is bounded in Ln sufficiently small, depending on this lambda. Okay, then you can run the same Ricci-DeTurck flow for some time, so that okay, now we don't have CCO convergence. So that's why we have something else. We can preserve the bi-Lipschitz, okay, a little bit. You need to sacrifice the bi-Lipschitz constant a little bit, and then the flow will converge back to the initial data in the W1n topology locally. So if M is compact, then you can drop the local, okay, and then like similarly, the regularization also holds, okay, in a scaling invariant way. So as you can see, this is scaling invariant. Okay, it's scaling invariant. It's also, that's why I said this is parallel to the CCO topology. Okay, the same things, the smoothness, and then we have the stability. Okay, the stability. Okay, okay. So I want to point out, although the theorem looks so similar, but the techniques involved is slightly different. But the moral idea is similar, although the techniques are different. So as I've said, the earlier result of Miles based on the fact that CCO convergence representing how close, how flat the metric is in terms of the metric cone. Okay, so if it's CCO, then asymptotically, this is like the tangent, this is like a flat cone at every point. So now the W1M structure pay the same things. Okay, if this is W1N, then when you zoom in large enough, if you zoom in the metric close enough, you can only see the Euclidean space because it's W1N. You can't, the W1N structure will force you to be almost Euclidean, okay, in the small scale. That's why you expect the regularization here, okay? The almost flat tangent cone in the W1N sense. Okay, this is a key point of everything. Okay, which substitute the CCO convergence information. Okay, so it's the argument is based on a concentration argument, which used a lot in other geometry analysis. Okay, but yep. Okay. Okay, and then based on this, we just replicate everything Balmer did, and then prove the preservation of a scalar curvature law bound. Okay. Okay.
Sorry, can I ask a question about the bounds? Like in item 3, like why is it that you get pointwise bounds instead of subalove bounds?
Oh, because first of all, the point is that you can prove that this bound is preserved. This one is preserved. the key point is to prove that the W1N structure is preserved under the Ricci flow. Once you can preserve the W1N, you can use the parabolic mean value inequality to improve it to the pointwise estimate. Yeah, this is the idea. Yeah, because you have some strong estimate here. This is the W1N estimate. Once you can, because it's a parabolic PDE, it's strictly parabolic. This is the key point. Strictly parabolic, you get some W1N preserved, then the parabolic mean value inequality will give you everything. Okay, and then you bootstrap it. Okay. W1N give you the C1, C1 give you C infinity. Okay.
Thanks.
Okay, so all right, this is one possible application, which is motivated by the question of Gomov, and then you can see now. At least you can see that how flexible and how useful the Ricci flow is to the scalar curvature problem, and then you may try thinking another. Try to find other application on all this, okay? Is because the regularization is just too useful here, okay? Okay, so the other application is to study the non-smooth metric, okay? Yeah, the setting is we start with some non-smooth metric on the torus. Okay, I use the torus just for convenience. It's the torus structure plays no roles. Okay, except for the rigidity part. Okay, so you can use anything else like sphere, like sphere spin manifold in the setting of sphere, asymptotically flat manifold, or torus. Okay, and then the moral question is, okay, suppose the metric is non-smooth, but only scalar curvature non-negative in the weak sense. Then can you prove that the metric is flat in whatever sense you are? Okay. For example, if you're a continuous metric and you have weak notion of non-negative scalar curvature, then maybe you can prove that it's a flat metric in the CCO sense or in the W1N sense, depending on which category you are. Okay, and then of course you can ask the same question for AF or for the spherical manifold. Suppose M is spin and the scalar curvature is bounded from below in a weak sense, emitting non-smooth distant non-increasing map. Then can you say that, okay, the metric is still weakly spherical, say for example? Okay, you can ask the same question depending on which class you are interested in, right? Okay. Okay, so let me point out a few options that we can. For example, this is option 1 by Lee and Lafleur, which I hope I haven't copied incorrectly. So to make sense of the definition, the metric is only required to be L infinity and W1N local. So by scalar curvature bounded from below, that means as in the distributional sense, which this is how they call it. If the inner product with any non-negative smooth function is non-negative, okay. So because it's inner product, we can make use of the fact that the scalar curvature is can be viewed as a divergence operator. I mean modulus some lower order term. Okay, so that's why we can formulate the scalar curvature lower bound weakly. Okay, by using the divergence formula for the scalar curvature. Okay, also this is very complicated, but basically I'm using the fact that scalar curvature is represented by divergence of something modulus the lower order term. Okay, all right. And then the option 2, which is proposed by Gomov based on his definition of a scalar curvature non-negative, is to impose the impossibility of containing a cube with strictly mean convex faces and require all the dihedral angle is less than pi half. Okay, and then of course I don't really like it because it's too geometric and very difficult to check. And then there's an option 3, which is quite related to the positive mass theorem with corner, which says that, okay, which is motivated by that question actually. So if G is smooth and L infinity with certain assumption on the singularity, and we require this out of the singularity, the curvature is well-defined and non-negative. Okay, then as you can see, if S is a codimension one, then it's reduced back to the positive mass theorem with corner. Okay, the more like the first case to be considered. Okay, and then the option four, which is like the summary of everything except for the second one. If G is a continuous metric, then I said the scalar curvature is non-negative if you can find some approximation which converge, which have the same or almost the same lower bound but converge in CCL topology. And then of course you can change it whatever you like the depending on what question you are interested in, you can change it so that it depending on whether you can get some interesting result, so you can change it. Okay, so then the question is, okay, among all this possible choice, which one is strong enough? I mean, by strong enough, I mean not too strong but not too weak to give you some rigidity. Okay, right? Yeah, I mean, if it's too weak, then it's pointless to think about all the assumption, the condition. I want to find something which is not too strong and not too weak to talk about the rigidity. Okay. This is my favorite. I like the option 4 because it's cover everything. Okay, I mean cover most of them. Okay, first of all, it's cover the option 1 if G is W1P, where P is greater than N. So in Ricci flow theory, this is not scaling invariant. So in some sense, you can pretend, in this case, you can almost like pretending G is smooth because it's not far from being smooth because P is better than critical one. Okay, and then you can expect this is almost like the good case, and this is in this case you can prove that it will contain inside the option 4. It's done by Jian Shan Zhang. Okay, it's based on Ricci flow. And then in the option 3, which is the case which allows singularity, which is motivated by the positive mass theorem with corner or with some singularity. Okay, then in this case, for example, if S is a codimension 1 smooth hypersurface, then and then with some constraint on the mean curvature on the hypersurface, and with some constraint on the regularity, then it will reduce back to the option 4 with you can find some approximation. Okay, this is I think it's done by Sakihide, and sorry, I forgot the author. And then if the singularity is of higher codimension, and the metric is not too singular, it's still very regular, then it's also done by Jian Shan Zhang. Okay, and in the critical case, which is the case when metric is only C0, and then the in the John Worth with Tam, we can prove that if the codimension is high enough, then we can also go back to the option 4. Okay. So the main idea is to produce the approximation using the Ricci flow smoothing. Okay. Let me point out, this is the key things. Okay. The idea is to prove, is to regularize, is to find the approximation using the regularizing Ricci flow. In this case, in the case when, in all the cases I discussed above, they're all continuous by Soboff embedding. So I can run the flow by the word of mouth and call NM, GIM, etc. The difficult part is to improve the scalar curvature lower bound to something smooth. Okay. When P is greater than N, the non-critical case, the metric behave quite well because the assumption is not scaling invariant, so you expect something not scaling invariant also on the smoothing. Okay, in this case, I haven't changed the power, sorry. Anyway, something strictly less than 1, okay, which gives you a lot of flexibility on improving the maximum principle, okay. And then in the case when you are interested in the distributional scalar curvature, you can use the heat kernel to prove something similar, okay. All right, so this is the idea behind the W1P part. And then the critical case, which is the difficult part, is done by myself and Tam, which prove that actually, even you don't have the estimate is scaling invariant, so that it's not integrable in time, but still you can talk about the maximum principle. You have the singular maximum principle, okay, which says that if your Ricci-DeTurck flow is moved for positive time, stay by ellipsis to some fixed metric, and then the estimate is scaling invariant, but with a really small constant here. And if the singularity is of high codimension, by high I mean strictly bigger than 2. Okay, I'm using the Minkowski dimension for the definition of codimension. Okay, if the scalar curvature is bounded from below, away from the singularity, then the scalar curvature will be instantaneously smooth and behave exactly what you expect. Okay, pretending the singularity is disappearing. Okay, basically, I'm saying that if the codimension is high enough, then the singularity will be unseen from the Ricci flow point of view. Okay, this is the optimal lower bound that you expect from the Ricci flow. Okay, so I want to point out one more thing. Okay, so you can see that I require the smallest on the regularization here, which is actually true under the CCO or W1N structure. Okay, why this is true? Intuitively, the delta here is measuring how close the flow close to the Euclidean spaces, the tangent cone. The delta is measuring how close the metric is to the tangent cone. Okay, it's very, very small scale, in the asymptotically small scale. Okay, so like I said, if the metric is CCO close, then of course you expect the flow is close to the flat metric in the asymptotically small scale. Okay, that's why you can allow the delta. That's why the delta is true here if you require T to be small enough. Okay, this is what I mean. Okay, this should be O1. The O1 is measuring how close the metric is to the metric cone. How flat is the metric cone? Sorry, how flat is the metric cone asymptotically? Okay. So because of this, we have some removable singularity theorem. Okay, this which says that suppose we are considering a CCO metric on torus. Okay, torus, and if the singularity is of codimension 3, in fact, it's only required codimension 2, slightly bigger, slightly higher than the codimension 2. Okay, but let me put it codimension 3 for simplicity. If the scalar curvature is non-negative away from singularity, then you can always find some other chart such that in terms of other chart, this is a smooth flat metric. Okay, by other chart I mean finding the distant isometry, which is smooth, which is a smooth diffeomorphism outside the singularity. In fact, the phi here is a C alpha diffeomorphism. It's a C alpha homomorphism. Globally, is a C alpha homomorphism. Okay, so which is based on the singular maximum principle that I just draw your attention, and then yes, yeah. And then in fact this the theorem is also conjectured by Rickson that the singularity is also removable for L infinity metric. That's why I'm interested in the L infinity setting. There's several reasons why the L infinity existence theory is desirable, although it's not. Although I don't know how to prove it, but yeah. I don't know whether it's true or not. But, yeah. Okay. And then when n is 3, the conjecture is actually true by the work of Lee and Mandolitis. They make use of the minimal surface, but wow, we are making use of the Ricci Flow. And yes, okay. All right. Any questions so far? Okay.
Can you exactly say removable in what sense in this conjecture? I missed the point. In conjecture.
His exact wording is very vague. So my interpretation is to find some other change the. I think he first of all, to my understanding, but although the way he put it is very vague, to my understanding, first of all, you need to prove that at least away from singularity, this is a flat metric away from singularity. At least you need to prove this one. And secondly, I think that means after you do some change of coordinate, you can reduce back to the smooth one. Okay, this is what I understand. Okay.
In the conjecture.
Yeah, but he didn't put it.
Any L infinity metric. Any L infinity metric.
Yeah, infinity. That means
change of coordinates which make it smooth. Or continuous.
Not continuous.
But what?
Like he consider the way he put is like sorry. He consider I should roll things like this. He consider metric like this. Yeah, I mean by L infinity, I mean this kind of metric. So that means the singularity model should be like a metric cone. Yeah.
But what means removable?
Sorry?
What means singularity removable? Meaning it like that. By change of coordinates, it becomes pinch between two metrics.
I think he means the thing. It depends on. He didn't put it very rigorously, so that's why I don't know how to answer you.
Okay.
Yeah.
The theorem that's written there can be the one that you have already. I mean, you can interpret that as a removable singularity.
Yeah.
So it's in the same sense.
Yeah, in this sense, yes. Yeah, but I'm not sure if he means the sense I will. Yeah, that is my concern. Yeah. I did in this. I in some sense I'm already saying that this is removable in the sense that up to modulus the distant isometry or modulus the homomorphism. This is a standard flat metric. Okay, modulus the diffeomorphism, modulus some Wolf diffeomorphism. It reduces back to the standard metric. This is how I interpret the question.
Okay.
Yeah. Okay. Okay, so let me move on to the sphere because one more thing. Sorry, I forgot to mention. In fact, you can see that the Ricci Flow approach is so flexible. We can even prove the same things. The torus structure actually play low roles except for the rigidity part for smooth case. Okay. As long as we have rigidity, as for smooth metric, we can prove the same things. So we can extend this theorem to negative Yamabe constant, not negative Yamabe invariant case, or any other vanishing Yamabe invariant case. Okay, you can prove the same things. Okay. There are no problem. Okay, but the proof of minimal surface only works for vanishing Yamabe invariant case. So yeah, that's why I want to advertise the Ricci Flow approach. Okay, So let me also mention one other application related to the spherical rigidity. So I have mentioned three rigidity related to the scalar curvature. Okay, so far I only consider one of them. Okay, the torus, and I want to also raise the spherical rigidity part. And in fact, it's a question of a Gromov, which asks, suppose M is spin. I think the way you ask is when G0 is a smooth metric, but the map is a non-smooth distant non-increasing map, which with non-zero degree. Okay, then Gromov asks whether the F is a distant isometry or not. Okay, so because you don't have smooth, so that's why you only expect something on the level of distant geometry. Okay, by distant, oh, sorry, I should mean non-increasing. Okay, as long you can see that as long as F is F and the metric is continuous, then the distant non-increasing makes sense using this. And to us, or in the theorem of Larrell, we actually interpret this by the tensor inequality. Okay. This is a key point of the theorem, okay, on the smooth analysis. Okay, so I want to mention this is a rigidity theorem which answers the question of Gromov, which is done by Cecily, Huang, and CUHK, and myself and Tam independently, but which says that the question is correct. Okay, the question is the answer is yes. Okay. Let me mention some distinction between our method. So our method is entirely different. So like in title of my talk, I'm using Ricci Flow, and then they are using the spin, the Dirac operator. So they try to rebuild the non-smooth analysis on the Dirac operator. So they claim their result is true for even dimension. I'm not expert in the Dirac operator, so I'm not sure why the odd dimension is so much more difficult. I'm sorry. And then because their method is based on the Dirac operator, so their method also works for the area long-increasing map. Okay, but they define weakly, of course. Okay, and then our method is based on the Ricci harmonic map heat flow coupled with the Ricci-DeTurck flow, and based on the classical theorem. Okay. So one more thing, in our approach, this is flexible enough for continuous metric. Like I said, in order to make sense of the question, you only need to make sure that G0 is continuous with suitable assumption with suitable definition of scalar curvature law. Okay, and F is non-smooth but continuous. Okay, so you can expect, you can ask whether this is true or not for continuous metric. And then our method is flexible enough for continuous metric with definition of scalar curvature in the sense of option 4, which is based on the approximation. Okay, option 4 is the approximation method. Okay, and then their method is based on the Dirac operator, which also work for W1P. For P bigger than N, I think it's P equal to N is also working, but I'm not so sure. Yeah.
So maybe I make a short remark about the even dimensional assumption and the Dirac method. So in general, so that's a little a nuisance of the method. I would say that for producing a non-trivial spinor field, you need a non-trivial or non-zero index. Atiyah-Singer index, and so this usually only works in even dimensions. And because of Euler characteristic of the sphere, which is non-zero only in even dimensions, and in odd dimensions it's 0. And in odd dimensions you usually have to apply some trick, and even in Larouille's original work, the odd dimensional case requires a separate discussion. And when you look at the paper of Larouille very closely, I would go as far as saying, actually, there isn't a complete proof in the paper. So you may try to figure it out. But I mean, the theorem is true, which is claimed in Larouille's paper. It's also, so the odd dimensional case is sure, so there is no problem with this. But how it's written in the paper, it's a little, yeah. I mean, of course, you can now start a discussion whether it's a complete proof or not. But in my feeling, it's not quite.
It's written badly, but the idea is right, because
yes, the idea is right. So the trick is
intermediate step of the proof, which works.
Right. So the trick is that you multiply the odd-dimensional manifold with a circle of the standard matrix times lambda squared, and then you set lambda to infinity. So you make the circle bigger and bigger, and in the limit, then you are basically down to the original case that you are dealing with. So the idea is right. No. I don't want to question this. And actually, so we are now also working on the odd dimensional case, applying similar tricks, and hope to be able to settle this case too. So it's a little more work, and we are trying to using spherical suspensions so that we can reduce it to the even dimensional case. But this requires additional work, which has to be done and which is not in our old paper. But it's an ongoing project.
Okay, thank you. I heard someone is also working on this, but I don't. Anyway, thank you for the comments. Okay, and go back to. Go back to my approach. I don't know the operator. I try to learn it, but I just don't have time to learn all of this. Okay, so before I go talk about the proof, the idea of using the Ricci flow, let me mention one consequence. This is one of the reasons why I pick up this question. That's why I want to point this out. This is a question raised by Xi in one of his papers. Which asks if omega is a domain in a sphere with smooth boundary, and metric G is G is a metric on the domain which is dominating the sphere. The scalar curvature is dominating the sphere. The mean curvature is dominating the sphere on the boundary, and the metric is equal to the sphere on the boundary. Then the metric must be the sphere. It's like the mean O conjecture, except we have this extra hypothesis. Okay, and then you can prove using the same using the rigidity that we proved that the metric must be the sphere, and then if the metric is if the domain is hemisphere, then we don't have to impose the boundary condition like this. Okay. The idea is quite straightforward, just by doubling and then apply the theory because everything is allowed to be non-smooth. That's why everything works here. So I just want to point out one application of this rigidity theorem.
So when you work with these manifolds with boundary, then usually you can also work with comparison maps.
Yeah.
Not just take a subset of the sphere.
Yeah. Exactly. Yeah. Okay. Okay, now let me spend 5 minutes. Am I have 5 minutes? I don't know. Okay.
Yes, you can have 5 minutes.
Yeah. Okay. So let me point out one tiny some remarks saying that why the Ricci flow is so useful here also. So it's very mysterious that although the scalar curvature geometry is has nothing, all the rigidity theorem has nothing to do with the Ricci flow, but the Ricci flow just plays so well in all of the rigidity theorem. Once you know the long-existent theorem in scalar curvature geometry, the rigidity part can be done by Ricci flow so easily. Okay, once you know the long-existent part. Okay, for example, the scalar curvature law is sharp along the Ricci flow, which is the basic idea of Ricci flow, and more importantly, in the setting of spherical rigidity, the distance is long increasing. So of course, your naive thought is, okay, you should not expect the same F will be sensitive to the deformed metric, right? Because the metrics change, the F is not changing, and then it makes no sense, right? So to fix it, we just flow the F again, just flow everything as much as possible. So you flow the metric, you flow the F, at the same time, but because I want to make everything as canonical as possible, so I deform it by the so-called the Ricci harmonic mapping flow. But now instead of coupling the G, I'm coupling the Ricci flow, the Ricci-DeTurck flow. Okay, it depends on whether G is smooth or not. If it's smooth, then I just couple with the Ricci flow. If it's non-smooth, then I couple with the Ricci-DeTurck flow. Okay, then you expect. Okay, first of all, the rescale metric have the same lower bound of the sphere. Okay, I rescale it so that the scalar curvature is bounded from below by the sphere, and then you expect it's essentially the same as the metric the H is a sphere. Sorry, okay, and then by the isometry given by the Ricci harmonic map heat flow. Okay, this is the expectation. And then we are able to do it. We prove it by tensor maximum principle. There actually are lots of versions of this. I just picked the simple version of this which basically says that if the target is a sphere or is dominated by the sphere, then the biellipsis constant will be preserved under the Ricci flow. Okay. In fact, it preserved in a really flexible way. For example, you can allow this to be lambda, not necessarily 1. This is the key point of everything. Okay, and then it's regardless of how the Ricci flow behave, because in more speaking, the Ricci flow is you allow the Ricci flow to be non-smooth initially. So in some sense, there are some singularity at time equals 0. So if the estimate depends on how regular the flow is, then it's useless in our question. So then, but you can see that it's very sharp. It just depends on the Ricci flow itself, the flow itself, and the ambient structure, the sphere. Okay, and then it's very flexible to allow the approximation. And also, this estimate immediately give us the energy of the harmonic mapping flow, okay, which give you all the regularity by the. I don't mean by the standard theory. Modulus some effort on the standard theory, you can prove this. You can prove the same analog of the Ricci-DeTurck flow, which says that if G is a continuous metric and F is continuous distant on decreasing map, sorry, long increasing. I keep making a typo here. Then you can find the Ricci harmonic map heat flow coupled with the Ricci-DeTurck flow, such that the flow will be regularized instantaneously and preserve the preserve the distance on increasing. Okay, and then it's close to the initial data in a very quantitative way. Okay, so because of this, you can expect. Making use of this one, you can just prove the rigidity theorem.
So at what point is it not possible to just assume area non-increasing?
Oh, this part, I tried it very hard. This part is not true.
Okay.
It's like the tensor maximum principle or the concave, the eigenvalue estimate, basically. Okay, when you try to estimate the eigenvalue, so you try to estimate the point on the boundary of the cone that you are interested in. So if you're considering the distance, then you are in good shape because you have all the eigenvalue estimate, because you are estimating the lowest possible eigenvalues. So that means at the lowest bound, you immediately have all the lower bound of all the lambda I. But if you talk about the area, you're talking about lambda I times lambda j, then you don't have all the lower bound of lambda I. You only have lower bound of lambda I times lambda j, okay, which give you some restriction, okay. Okay, but okay, for the time being, I'm just skipping it. I'm just saying that, okay, to do it, I just regularize by elliptic smoothing of the flow of the map by green rule method. Then I flow it. Okay, then I get estimate. That's all. Okay, this is the standard procedure, except I mean, not by standard, I mean modulus the classical theorem by Green, but classical method of Green and Wu. Okay, and yeah, and finally, I want to point out one more application, making use of the time zero regularity of the Ricci flow, which is related to the question of Gromov, but this is not satisfying enough, but is one possible answer. So So we are interested to ask the stability question of a torus, which says that, okay, suppose, okay, just ignore the setting here. It's just basically saying that if the scalar curvature is almost non-negative, then in what sense is close to the flat metric on the torus, say for example, okay? And I personally interested in the setting like this, the assumption one, because it's so common in Kähler geometry. That's why I take a look on one, the long collapsing and on long expanding assumption 1 and 3. Okay, but I can't prove anything, so only based on 1 and 3. So I try to assume the energy is small enough in W1N sense, then we can prove that the sequence will subconverge to the flat torus in the LP sense for all P modulus the diffeomorphism. Okay, yeah, this is another possible application of Ricci flow on the stability problem. Okay, and it's just a simple comparison when the topology is C0, then it's well understood. So we are just trying to find the analog of this or some counterpart of this. Okay, let me stop here. Thank you.